I pushed it.
There we go. Excellent. Thanks for that, Jeremy. Thank you, everybody, for joining in today. My name's Janine Price from Scalexia. We're a consulting firm that was involved in the biosecurity, pathogen and environmental work on this project, and also some of the extension. I'd just like to let everyone know that, yes, we will be having, you can ask questions, and if you can put them in the Q&A box at the top right-hand side of your screen, the two talkie bubble marks with the question marks, if you could put them in there, and then we'll answer them at the end of the session. And we're also recording this, which we're hoping to make available to participants at the end. So if you have any objections, if you could let us know, that would be fantastic. And I will now introduce Matt Deegan from the Meat Processing Corporation, and he can give a bit of an introduction to himself and why the processing sector have been involved in this project. Thanks, Matt.
Thanks, Janine. So AMPC, we're the Research and Development Corporation for red meat processors in Australia. And we've been really interested in the work so far on the black soldier fly and its ability to convert agricultural manures and waste byproducts into fertilisers. Resource efficiency is really important for our members across Australia. And most solutions that we know of are in the chemical or biological space as far as conversion to fertilisers. This is the only one I know of that uses an insect, so it's quite novel in its approach. So I'd like to hand over to the first presentation by Sasha Jenkins of UWA. Thanks, Sasha.
Thank you. Okay, welcome everybody. I'm going to give you a bit of an overview about the whole project. So this is Closing the Loop, black soldier fly technology to convert agriculture to waste. It's a collaborative project between industry, academia, consultancy and government.
Sorry, Sasha, you've got the wrong screen up. You've got an email at the moment.
Oh. Really? Okay, sorry. Sorry. I'll just stop sharing that one. Yeah, sorry, I've changed to turn my email off, and then obviously I didn't flick back. It's done it again.
Nope.
Nope, it's done it again. Sorry, let's try again. Be carefully this time. There you go. Is that the right one?
That's the right one.
Oh, thank God for that. Okay, here we go again. Closing the loop, black soldier fly technology to convert agriculture to agricultural waste. As I said, it's a collaborative project between industry, academia, consultancy and government. And just at the bottom of the screen is all our partners that were involved in this whole project. I'm just going to provide this overview slide so we can get an idea about what people did and how they contributed to the project. So starting at the bottom, Luke Week from Feeder Green Solutions, his main role was to take all the different livestock waste and optimise rearing black soldier fly larvae on that, and with the ultimate aim of maximising the reduction in waste volume. So that's the first part. Once the insects are reared on the livestock waste, we end up with two co-products. The first one is the larva itself, and the larva can be basically split into two components: the fatty acids, which can be extracted and developed for other products such as biodiesel. In this project, we also used it as a coating material later on to sort of slow down the release of some of the frass, which leached a lot of, to reduce the leaching potential of it. The other component is the protein. So because these flies are fed manure, it cannot go back into the food chain. So we need to find another way of utilising that project. And Dr. Matt Redding at DAF Queensland will talk to you a little bit later about how he developed that larva as a really good fertiliser product. The second product that comes off of the black soldier fly technology is the larva frass, or essentially fly poo. This also has mineral N and carbon in it. And so what we did at UWA, my team, looked at basically developing this as either a soil fertiliser or soil improver. Also at UWA was Marit Kratz and Faye, who did the total economic and market analysis of this project. And she'll talk about, Faye will talk a little bit about that later. The other people involved were Scalexia, and they provided, Janine Price is the lead, they provided environmental and biosecurity risks analysis, and they also looked into regulation of getting these products onto the market. Finally, we had David Cook from DPIRD, who is a stable fly expert, and he did a whole range of analysis on looking at the potential of stable fly emergence from frass that have been applied to land, because obviously when we're producing products, we don't want to make that situation worse. So we'll talk a little bit about that later on as well. So the overall objectives of this research project were to develop the black soldier fly technology as a sustainable livestock waste management option to rapidly reduce the waste volume. So basically the volume, but also do it very quickly as well. And Luke will talk about that shortly. The next part was to take those two co-products, the protein and the frass, and turn them into low-cost tailored fertilizers. And myself and Matt will talk about that a bit later in the presentation. I will also touch on how we quantified some of the biosecurity environmental risks associated with applying frass. And Faye will talk about how we investigated the market potential for the black soldier fly products, and also finally look at some of the how we overcame some of the barriers to adoption. So that's around biosecurity risk, the regulation, and also public perception. And now I'm going to hand over to Luke, who's going to tell you a bit more about how he developed the black soldier fly technology to really quite successfully reduce the volume of different wastes of livestock.
Thank you very much, Sasha. So thanks, Sasha, Matt, and Janine for the introductions. Before I get started, I just want to sort of state how much of a amazing collaboration this has been. It's a really broad cross section of our agricultural players in Australia, across pork, dairy, the egg guys, meat producers, and also the fisheries. So it's been a really great collaboration, and that collaboration has been backed by some really amazing scientists across UWA, consultants at Scalexia and Matt Redding over at DAF Queensland. So yeah, really great team and really good outcome. So looking forward to Sasha and Matt presenting their results shortly. I'm Luke Wheat. I'm the founder, CEO of Future Green Solutions. We're a commercial insect producer based in Australia. And really my role is to introduce insect farming at a high level, to give the rest of the research presentations a little bit more context, as well as to give an overview of our involvement in the research project. So what is a black soldier fly? Soldier flies are quite different to what you would imagine when you think of flies. We think of house flies and stable flies and all those things that annoy us and cause damage to crops and livestock and people and other things. Soldier flies are actually a solitary fly. They have no feeding mouth part as an adult, so they don't feed as an adult, so they don't bite, they don't feed on waste streams, and then so they're not known to be a disease vector. They're also a solitary fly, so they're not known for swarming. And if you see them in nature, you may even mistake them for a wasp because they're quite a large, slender black fly. And they've been domesticated globally now for mass rearing. The larvae, because they're not feeding as an adult, the larvae are very, very efficient at converting organic waste streams into high valuable proteins and fats, which is essentially the part of the life stream that we commercialize most for the protein and oils if we're using other organic streams outside of manures and farm mortalities. So this is again a high level overview of a black soldier fly processing farm. So just like any other livestock industry, be it poultry, red meat, swine. We have our breeder farms to support the genetics and the flow of the population. We have a big focus on nutrition for the insects, and then we have our commercial grow out and processing stage of the facility. The only real difference is that the industry's in its infancy, so we've got a long way to go in terms of refining some of our processes, and also our genetic selection, which we can see the advances that the other industries have made in that regard. The process is all enclosed, it's very highly controlled, and can be done on a very small footprint. And if you can imagine, we have hundreds of millions of livestock, if you like, in a facility at any one time. So at Future Green Solutions, our mission is to give waste a purpose. Traditionally, that has been around predominantly pre-consumer waste from horticulture and food processing. And from those waste streams, we produce protein and oil as feed nutrition inputs for the pet feed industry, aquaculture and livestock. We also supply seed stock to other commercial insect farms within Australia in the form of eggs. And the FRAS product, which is the biofertilizer, which Sasha and Matt Sasha will talk to a lot, and Matt will talk how we applied a different market lens for the protein. So just to reiterate, when we use manures or farm mortalities as an input for the larvae, then the feed market products can't go ahead because of the biosecurity concerns that Sasha mentioned. And so we're looking at what are the other markets that we can value add into using the same technology. So really the question overarching this project was, can we take existing commercial insect farming technology and knowledge and convert that to more problematic waste streams that are generated in our agricultural industries? So how do we adapt? Well, first we'll start with the substrates. Manures and farm mortalities are a little bit new to the Future Green process. And so our initial screening was to look at what are the physical and nutritional properties of each of the substrates coming through, and how conducive are they or aren't they to insect rearing. So we looked at things like moisture content. Is it too wet? Is it too dry? What's the digestibility like? In particular, the paunch coming from abattoir waste is very, very high in lactose, which is not immediately digestible by the insects. A lot of the substrates were very low in protein and high in ash. And some of them had really challenging physical properties, particularly egg egg waste streams as a standalone product, as well as the fisheries waste as a standalone product. Now, typically we would never use a standalone single stream. We will blend where we can. And many farms and agricultural practices will have multiple waste streams on one site. So for example, in the swine industry, you might have farm mortalities plus manure on store and separated solids, et cetera, through the other agricultural industries. Now, just because a substrate's too wet, too dry, high in cellulose, whatnot, doesn't mean that we can't rear insects on it. It just means we put a little bit more thought into how we adapt that to get a better result. And so that could be that we're correcting the moisture. We can adapt our larval feeding rates. So if you can imagine, because it's poor in nutrition, we would feed them more than we typically would on a nutrient-dense diet. Can we do retreatments to the substrate? We looked at biological, enzymatic, and physical treatments of waste to increase digestibility, and also increasing the exposure time to which the insects were on the substrates. So overall, we had really rapid and significant waste on these streams to compare to traditional composting, which might take several months. We achieved this in just over 2 weeks, or around 3 weeks in some cases, and we got to 80% waste volume reduction in that time, with the exception of the dairy accumulated solids, which are composted on site for a few months first. And you can see the difference with the fresh dairy manures. We had much greater results, and the paunch again is very high in lignocellulose, so not particularly digestible by the insects. But I do want to point out, just because the waste volume reduction was less in the paunch, it doesn't reflect that the FRAS product was poorer. It will still be very high in carbon and very high in the microbiome that both Matt and Sasha will speak to in their presentations. So in summary, I think there's some really promising really amazing foundational science behind the project. We've achieved very rapid and significant waste reduction. The FRAS product is significantly lower in odour than manures. We've had reduction in greenhouse gas potential of in soil products. We've ended with a soil ameliorant in the FRAS that has clear plant health benefits and soil health benefits, as well as increased drought tolerance. And we had some really great results from some stable fly emergence trials, which Sasha will talk to in more detail in her presentation. So to close off, I think, again, I just want to thank all of the participants in the project. It has been incredibly collaborative. We've got some really great results, and I'm hoping that that fosters some continued partnerships moving forward. So that's something we really value at Future Green, and I think something that's really going to help an emerging market expand with confidence. Thanks very much.
Okay. See the screen? Yeah. So the next part of the presentation, I'm just going to focus on FRAS development as a soil amendment. So I'm just going to talk about this bit and a little bit about some of the environmental and biosecurity risks. So this is the part I'm going to focus on. So I'm going to look specifically just about the lava FRAS and its applications as a soil improver fertilizer. So objectives of this part of the research was to develop the FRAS as a low-cost, tailored, slow-release granulated fertilizer product that was safe to handle, store, and transport and apply. The second part was also to make sure it didn't have any biosecurity or environmental risks when it was applied to cropping. So methodology. So we did a range of pot and field trials, and this looked at all the crops, so varieties from horticulture, the grains and pasture. We then did a series of soil incubation experiments, and that was just largely to explore, to try and better understand how the FRAS was working. We saw benefits in the field and pot trials, but we wanted to understand what the mechanisms behind how the FRAS was working to get that enhanced growth or soil improvement. We also looked at greenhouse gas emissions from when we applied the amendments to soil. And we did a range of pathogen testing, and also stable fly emergence was also assessed. We also looked at whether we needed to further granulate the product or process it in another way. So for some of these samples, they were quite high in ammonia. So we actually added some of that fatty acid that we extracted from the larva to slow down the release of the nitrogen into the soil. The key findings, so obviously Luke has just said that we were able to really reduce the volume of waste by up to 70 to 80% across the livestock industries. The other key thing was that we saw a demonstrated reduction in pathogens. So the first table at the bottom is got the fecal coliform count for some of the industries. So we've got the pork, poultry, dairy. And what we see is a decrease in the, from initial coliform counts in the initial manures. When it's being fed to the black soldier fly, we see a significant reduction in both the larva and also the FRAS. That you see. The second thing was that we looked at applying the FRAS to land, and we did a range of field trials where we assessed to see what the stable fly emergence would be. So we added a range of application rates from 1 to 10. Usually we recommend around somewhere between 1 and 5 tonnes per hectare. And in that range, we just weren't seeing any stable fly emergence at all. We did see a few at the high application rates, but it's very, very low, and we wouldn't normally recommend adding at that rate anyway. But you can see compared to manure poultry, it's extremely high in the untreated manure, and the FRAS, processing it through the black soldier fly greatly reduces. So there's something about the FRAS that actually detracts stable fly from being able to establish in the soil. Another key finding was when we did our field trials in horticulture, pasture and grains, we found that although the frass couldn't completely fully replace N fertilizer, it was able to partially replace the N fertilizer. So it provides some of the N, so you don't have to add as much fertilizer. So that's obviously a significant reduction in fertilizer that you're adding. On the bottom left, we've got the photos of the field trial, and we've got red clover, ryegrass, wheat and canola, and across the top we've got basically increasing concentrations of frass applied. And I think we can all see that as you add a higher concentration of flashes or application rates added to the field trial, we can see that there's an increase in yield. So we are definitely getting a response in improved crop production there. The other thing that was really pleasing is that we actually saw that the frass also improved the condition of the soil. Particularly, it raised the pH. So this is very significant for our soils because they're very acidic. So it really can increase the pH of the soil. So therefore, the farmer wouldn't need to add as much lime potentially. And the other thing that's really important, it was able to tolerate help the plant tolerate water stress, both in the field trials when we were doing the irrigation trials and non-irrigated trials. Plants that received the frass in the non-irrigated trials performed a lot better. We followed up with some targeted pot trials, and here's one of the examples here on the right-hand side. So here we've got basically a frass response curve to drought. So these plants have been droughted, and they've been amended with increasing concentrations of frass. And I think we can see as we add higher concentrations at the 15 and 20% volume, we see a much more significant plant growth. It seems to tolerate the water stress a lot more. So that's also a really positive finding with the frass. Other key findings was that the frass, when it was applied to the soil, particularly in the field trials, it was increasing the soil carbon. So this first figure shows soil carbon against application rates. And as you can see, as we increase the rate of frass applied, we see a gradual increase in the soil carbon. And this is only after 1 year of field trial. So we are actually seeing that change in soil carbon after 1 year of field application of frass. The other thing was that we saw a reduction in odour. So the frass itself does not smell, it's pretty nice compared to other products on the market and also the raw products. It also reduces the greenhouse gas emissions, and also in the leaching trials, we were able to basically putting it through the frass, so putting the manure through the insect, which greatly reduced the frass. And as I say, we also had our ways to even increase that further, that leaching potential further, by coating them with those fatty acids extracted from the insects. The middle graph shows nitrous oxide against time. What I want to focus on here is the manure in the blue and the frass in the yellow. And I think we can see that by basically applying the manure to insects, into the frass, and producing the frass, we can see there's a greater reduction in the greenhouse gas emissions. So the frass is producing almost as half amount of nitrous oxide emissions that the raw manure produced. Finally, we were successful at granulating it. Here's an example here of the granulated product. We also looked at pelletizing, so there's a whole range of things we looked at to sort of improve the product to reduce its transportation costs. So what's the implications? Obviously, Luke has touched on its improved management. It's a sustainable pathway. It reduces the waste by up to 70 to 80%. Aside from that, we also have increased productivity and probability because we've got these generations of these new products that can enter new markets, whilst also reducing the on-farm costs associated with waste management and fertilizer use, if the farmers are using fertilizer. Reduced biosecurity risks. Well, obviously we saw a reduction in pathogens, and very pleasing, there was really just literally no stable fly and other nuisance flies produced. And that's really important in WA, particularly because a lot of the industries have lost markets where they used to be able to apply their manures, particularly in horticulture. So it may be there is an opportunity to regain those markets. And during this project, we have engaged with the Stable Fly Action Group. We also saw enhanced soil benefits. So aside from reducing greenhouse gas emissions, we saw improved health in terms of soil carbon. We saw beneficial microbes, and we also saw increased nutrition, increases in the pH, and also how the plant dealt with water. So it's much more water efficient when it had been amended with FRAS. Where to next? One of the things that came up when we talked to some of the industry farmers was they were looking also, some don't want to produce a fertiliser, so they did actually ask, is there alternative pathways for the FRAS and larva? And there's actually lots of opportunities and lots of other pathways where the FRAS could be developed as something else. One possibility is developing it as a waste energy product, which was one of the things that was mentioned quite a lot. Can we produce it as an energy product? And yes, it does seem that, certainly from the literature, that both the FRAS and the larva are good substrates for that. But aside from that, there's certainly a lot of literature around and other industries doing this around bioplastics and even as cosmetics. So there are different options, and that could be explored a bit more. Further evaluation of the FRAS is needed, particularly around the restoration. So we found that it really improved soil under sort of less under soil where the plant growth was constrained. It seemed to certainly improve. So we can maybe expand that a little bit more and see if it can be used as part of rehabilitation or restoration. Finally, I think we need to do a full life cycle analysis of the greenhouse gas emissions. So we certainly saw a reduction in greenhouse gas emissions from the applications of the larva and also the FRAS, but we haven't done a full life cycle analysis of all the production cycle, and this is particularly important in terms of carbon credits. So that's from me. I'm now going to pass over to Matt, who's going to provide a bit more information around developing the larva as a fertiliser.
Well, I'll just select the correct presentation, I hope. Right, there we go. Yeah, I'm Matt Redding. This title of this one's about larvae as a fertiliser, and the reason why I was particularly interested in the potential there is it's a proof of concept trial, but it's also using a material that has considerably condensed the nitrogen content relative to what's in many of the wastes that might be fed to the flies. The team working on this has included myself, Sheikh Rabi, Brianna Smith, Armando Navas, and Tara Rogan. So that's a team that involves both soil scientists, biogeochemical capability, and mechatronic engineer in it. And you'll see why in a moment when I show you the types of techniques that we apply in this research. This is sort of my extremely long subtitle for the project. We're looking at larvae as a fertiliser. We also look at other things, details from some other projects. But what we're trying to do in essence is work out if by feeding the soil microbes, we can help synchronise the supply of nitrogen with plant needs and better achieve nitrogen use efficiency. That's what it boils down to. One of our key guiding principles here is pretty logical when you think about it, and maybe not. Maybe it loses some of its impact after you've been looking at it for a while, like I have, but it's still extremely important. This idea that conventional fertilizers tend to follow the red line, where soon after applying the fertilizer, you have the greatest availability of that nutrient. It's sort of sloshing around in that soil environment where it is highly vulnerable to losses, and yet later on in the season, when there's peak requirement for that nutrient by the plant, which tends to follow the blue line in this diagram over the season, where of course the germinating plant doesn't require as much nitrogen initially, but much more later on, the two profiles are almost exactly opposite of each other. And this leads to this issue of only 40 to 60% of the nitrogen applied in conventional fertilizers being taken up by the plant. And in fact, in some Australian production systems in wet years, it can be as low as 15%. So the techniques we look at this, and remember, we're trying to work out the synchronization of availability with the release from the plant, from the release from the plant with the requirement, release from the fertilizer with the requirement of the plant. So we have to be able to do some fairly, we need to be able to measure the release over time, and we need to identify how that interacts with the plant. So the techniques we apply are these reaction vessels initially, where we put microdialysis probes into the soil. We measure gas emissions via online real-time techniques. And you can see here, incidentally, this is the larvae in the soil, lots of fungal development. That might sound bad, but actually it can be a really good thing to have fungal activity to break down the nutrients in the larvae to make them available to plants. We'll talk about that a bit more later on. This is an image from our growth accelerator. You can see the plants there are about 120 plants grown at a time in the pot trials inside that growth accelerator, which is robotically watered. But also we collect these 3D scans of the plants growing. Now, why do we do that? That's mainly so that we can work out the ongoing release of nutrient to the plant. It's all about measuring that synchronization. And of course, we progress on to field trials. This is from a sort of related project, a field trial that we conducted, and I'll talk about the data that comes out of both of these projects, and I'll give you the name of the other project in a moment. So we have that idea of synchronization being the goal, and this leads us to another guiding principle. This was a pretty inspirational quote that came out of a paper from 2007, and I've had this idea in my mind ever since, and I guess there's been many other people too who have. So the inefficiency that we see with the use of conventional fertilizers is a consequence of the uncoupling of the carbon, nitrogen, and phosphorus cycles via the use of highly soluble fertilizer forms. This results in agricultural ecosystems being maintained in a state of leaky nutrient saturation. So our concept for starting to combat that and to recouple those carbon and nitrogen cycles is to seek to first feed the microbes in those soils. Now, just to elaborate that out to a more sort of complex idea, but to cover exactly what I mean by that, that we sort of think that perhaps by manipulating the ratios of carbon, nitrogen, and phosphorus and the other nutrients, we can influence biomass development, that's microbial biomass development in the soil, the biomass nutrient utilization, and the release of nutrients. And that by targeting a sort of optimum soil microorganism ratio and providing a sparing excess above that level, we might be able to control the turnover of those nutrients and how they're released to plants. So we know we're talking about this Black Soldier Fly project, but there's also related projects, the Smart Farming Partnerships Pilot to Paddock project, and you'll see some results in these coming graphs here from that project as well. Okay, so this is what we call a multivariate analysis graph, where we relate a wide range of factors and variables to outcomes that we're interested in. You don't need to know much about that. The main thing is that this fertilizer layer carbon to nitrogen ratio, the arrow here is closely aligned with the ongoing nutrient uptake from the soils. So why is ongoing nitrogen supply most related from our findings to the soil's carbon to nitrogen ratio? That's the soil in the fertilizer zone. So we believe that's because there's a sweet spot for soil microbes. Righto. So these are average plants from a set of replicates in one of those pot trials in the growth accelerator. I've graphed up as the plant that represents as closely as possible the average of those 5 or 6 plants. So here we have pots that have all received all the other nutrients they might need. And so that's phosphorus and trace elements and so forth. And the control has received no nitrogen, but all of the other pots have received the same total nitrogen application, except in different forms. So this one has received urea, conventional urea application. This one's received an organic product that's already on the market. And this one has received our modification of that, where we've modified the ratio of carbon to nitrogen. The key here is that these two really aren't performing that well. The urea is performing as we'd expect it to be, quite well, except that you can see this modification of it later in the last few photographs presented is actually accelerating past the urea performance. So that's an example of us, of one of the formulations delivering better nitrogen use efficiency than urea. The question is, how difficult is it to do that? Well, here we have in a graph of nitrogen uptake for 2 harvests and their total. So that's 0 to 44 days production. That's 44 to 120 days production in this particular soil. That's urea. That's a formulation of larvae. And you can see in those description of treatments along the bottom, I stands for a nitrification inhibitor. That these two, you can see these two have exceeded urea performance, as have these proprietary extracts of larvae completed by Future Green Solutions. And in fact, we have a range of other treatments that are also capable of outperforming urea. This is a different soil, a different, basically the same set of treatments. Dry matter production in these 2 graphs for 2 harvests and nitrogen uptake in this one. And yet again, you can see a whole range of treatments that exceeded the performance of urea. However, and this is how soils tend to differ. Later on, production in that second harvest with ongoing release from that particular soil was considerably more important than from in this particular soil. Urea N is extremely vulnerable to losses. And you can see that straight away in this graph of nitrogen leached. So our pot trials had a leaching challenge applied to them. And you can see that urea is here, and it's as large or larger than every other treatment that we listed. Some of our treatments weren't that great either. Statistically, they're about the same as urea's losses, but we had many that were better. And of course, what you want is to minimize your leaching or runoff losses from a fertilizer, so that then you have the best chance possible of ending up with that nitrogen in your plant. So our evidence is unfolding that soldier fly larvae and some of the other circular nutrient economy products can be formulated to end up with more of your nitrogen building up the soil microbial biomass. And that enables us to better synchronize the supply with plant need. The carbon to nitrogen ratios that we've been exploring have ranged in the soil profile. So that's this carbon to nitrogen of the, what would we call it, of the fertilizer zone within the soil, ranging from around 8 up to over 13, I think. And the ratio that you choose is dependent on what sort of turnover time that you require, and that can be tailored. So we're able to increase the biomass. That also tends to decrease the waterborne losses, improve nutrient use efficiency, and we can also build what I think of as more resilient soil profiles. Whereas with conventional urea application in a soil profile, in some production systems where there's a lot of runoff or leaching challenge in the field, you can end up with all of your nitrogen disappearing very quickly. If you've built up the soil microbial capacity to turn over nitrogen and continually mineralize nitrogen, those events will be far less catastrophic to your production. And we're also able to increase the retention of carbon in the soil profile. An interesting thing we're delving deeply into at the moment is what is the impact of these formulations versus urea on the retained carbon in soil profiles. It's known that in some production systems, urea addition can actually decrease the soil carbon because of the microbial activity, having nitrogen on one hand that's readily available, but they need some fuel to sort of process that nitrogen. So they take some of the old soil organic matter and break it down. So urea performance is really not impossible to beat. And we're continuing working in this area to develop more and more practical fertilizer formulations. Thank you very much.
Thanks, Matt. We'll now hear from Faye.
Thank you. I'm just trying to share my screen. Can you see my screen?
Yes.
Okay, perfect. Thank you. Okay, good morning, everyone, or good afternoon, depending on where you are. My name is Faye Rolla Rubsen, and I'm an associate professor at the School of Agriculture and Environment and the deputy director for the Center for Agricultural Economics and Development at UWA. So the focus of my presentation today would be more on the adoption side as well as the marketing potential for BSF. So our team actually is comprised of several agricultural and resource economists led by Marit Kratt, and we also have Dr. Vandana Subroy, Fiona Dempster, and myself. So our focus is actually to investigate the adoption barriers and market potential of BSF products, because basically we are the second half or the second half of the the technology part, because technology will be excellent, for example, but then the other half of that is will actually the end users use it. Okay, so the methodology we use is quite common, common methodology that we use in economics when we're looking at adoption and marketing studies. So we first look at the literature on what has been done already on this area, in particular in marketing and also adoption of black soldier fly. And what we found is that there's really not much yet in this area. Most of the studies are actually in North America and some in Africa and Asia, but not much on the marketing or economic side. We actually also then, from the literature reviews, we develop questionnaires to interview livestock producers and potential end users. We also did an industry-wide survey with end users, and we did a benefit cost analysis. So in terms of the waste producers, what we looked at are the cost of livestock waste management. And when we say cost, these are both the economic cost, the financial, for example, the cost of stockpiling, collecting the waste, and general management of the waste. But we also look at the non-financial costs, such as the odor, the nuisance cost, the GHG emissions, as well as the health impacts of waste. And what we have found is that the costs are often not clear. In fact, many of the producers do not really formally collect these costs. So it's just they just consider it as a part of their normal everyday activities, and so it's not really collected. And the other thing we have found as well is that the costs are highly variable between the different livestock systems. So from chicken producers, for example, to piggeries and to pastoralists. So the costs are actually really variable in the industry. But what we have also found out is that they are interested in using black soldier fly for their waste management. They actually have a positive attitude towards BSF technology and are quite willing to try it. But we still need to develop options for on-farm application because there are, of course, the cost implications as well as the biosecurity concerns in terms of, using BSF on their farms, using the BSF frass on the farms, as well as in terms of, the transport issues. In terms of the end users, so the next question we had was actually, is there a market for BSF fertilizer products? So there are actually already some products available in the market, but these are often in smaller quantities, so smaller packages. So for example, if you go to Bunnings, you will find some of these products already available in the market. So what we have done to find out, to value BSF is we use methodology that we use in economics called non-market valuation. So essentially what we are looking at here is what's the willingness of end users to pay, looking at different attributes, product attributes. For example, what form of the products, whether they would prefer fine particles or granules, and then also their organic carbon content. And we use the values of 60% and 40%. And also the NPK content. So we had low, medium, and very low. And then for price, we used from $150 to $1,800. And this is not really based on the actual cost. These are actually things that we have designed to look at very low value to very high value and medium value as well. So in terms of the results, so what we have found out is that farmers are interested in using BSF FRAS as a soil amendment. So BSF FRAS is, if you compare it with the synthetic fertilizers, it's unlikely to be competitive at current market prices. Also, it's low NPK content and low bulk density. And of course, there's also high transport cost. Nevertheless, all of the farmer respondents indicated that they were interested in testing BSF FRAS as an additional organic fertilizer or as a soil improver. So alternative farmers in particular are very interested in the product. So this includes, for example, regenerative farmers. They really are very keen to use and try BSF in their farms. Okay, some in terms of some final thoughts. So generally our findings show that there is a potential market for BSF products. Farmers have a positive attitude towards using BSF technology for livestock waste management, and they are actually really keen on using BSF as a soil ameliorant. And the next steps, however, is that we still need to find whether there is a potential to use BSF technology on farm to overcome waste transportation constraints. So that's one concern that came very clearly in the research. And also, with the price of BSF fertilizers, meet the end user's willingness to pay. So at the moment, the cost of fertilizer is quite high. It's commercially available. FRAS fertilizer products are commercially available between 1,500 tons to $3,000 per ton, depending on the specific product customization requirement. They're also commercially available blended FRAS fertilizer products, such as blends of BSF FRAS with biochar, and that retails actually in high volume agriculture market for around 2,200 per ton. So whether the users will be willing to pay for that is a question that we need to investigate further. And finally, we also need to involve policymakers to overcome some of the regulatory barriers in implementing this and in terms of the adoption of BSF fertilizer products. So that's it. Thank you very much.
Thank you, Faye. We'll now go to the Q&A. I'll start from the top and work down. So, Matt, what was the chemical composition of FRAS protein fat, and what is the form of nitrogen? I might just say before we start that the project results, the project has been put into the Commonwealth for review at the moment, and there will be a video, fact sheets, and various journal articles that will come out of this project, but they're just in the process of being reviewed at the moment. So some of the commercialization and IP things are still being reviewed. So our researchers will do their best to answer the questions the best they can at the moment. So, Matt, could you answer those questions that have just been asked of you?
Was it on FRAS or was it on larvae or what?
What is the chemical composition of FRAS, the percentage protein?
No, you better ask Sasha that about the FRAS. I can have a look at what the larvae was.
Yeah. What is the form of nitrogen chemical entities? Protein, question mark. Is that for you?
Yeah, they're going to be complex that are in the larvae.
And I think, sorry,
and
Matt, just to jump in, I think some of these questions we might just have to put on hold for now because some of these are going to be sort of commercial in confidence questions.
yeah, right.
How would you control microbial metabolism for slow fast nitrogen release? I think that's more Sasha.
Yeah.
and-
Well, so frass. Oh, okay, not larvae.
Yeah, I think it's more frass.
Well, I'll tell you, for my work with the larvae and the proprietary product from it was by changing that carbon to nitrogen ratio and ensuring everything else that the microbes needed was there. So you can find for a particular system an optimum for the plant that you intend to grow in it. And that depends on that uptake, that ideal uptake profile for the plant is of course for different crops. And since you're also juggling the carbon content of the soil, you have to take that into account. But over to Sasha for the frass question, first part of the question.
Excellent. The next one is, can you please provide contact details for the speakers? We can do that, and we'll also share the videos as well, and that's got everybody's contact details, I believe, on them as well. Sasha, I'm not sure if you can answer many of these questions, the pH of the frass and how much soil pH was raised and how much nitrogen was in the frass.
Sorry, I'm choking. I'm not 100% well today.
Oh, that's not
Do you want me to go for the next one?
Yeah, sorry, I'm not 100%.
Yeah. Was there a preference for paunch from grass-fed or grain-fed, or was there no difference? Luke, you might be able to answer that one.
Sorry, Janine, do you want to go again on that one? I was just answering a separate one in the chat.
Was there a preference for paunch from grass-fed or grain-fed, or no difference?
Yeah, so the paunch that we received was mixed source. If I was to hypothesize, I would suggest that the waste reduction will be higher in grain-fed versus grass-fed. But again, the waste reduction isn't a reflection of the performance of the resulting frass products. But that would need to be looked at in more detail if you wanted to differentiate between the two in terms of performance.
What is the output ratio of protein versus fat? That's another research project that's probably being reviewed. I think you've answered some of these questions. These ones have been 100% of the inputs become saleable product at the end of the process. And then there's, as you said, there's the publications being reviewed at the moment. Was there any other questions in the chat or any that haven't been answered? Yeah, taking into account that the project's currently with the Commonwealth being reviewed and the journal papers are being reviewed and everything at the moment.
Yes, there are 3 or 4 questions in chat.
Okay. Just trying to go up to, there's quite a few. Just going down. I would like some clarity on which of the process output treatment methods presented achieved fertilizer products with novel controlled delivery, nitrogen transformation inhibitors, and plant growth promoting rhizobacteria to ensure increased nutrient uptake, which was the project goal number 1.
Hang on. I have to read that again.
Any takers?
No, I'll have to reread that because it's quite a long thing. Where was it?
In the chat, perhaps.
Yeah.
Which of the process output treatment methods presented achieve fertilizer products with novel controlled delivery, nitrogen transformation inhibitors, and plant growth promoting rhizobacteria to ensure increased nutrient uptake?
That sounds like a bit of mixed up of a couple of things. All right. So we've done work on investigating whether there are plant plant promoting rhizobacteria in some of these materials. We've found organisms that sometimes are related to that across both those projects, the Soldier Fly project and the Smart Farms project. However, they're not apparently the reason for the performance we've got at the moment. Now you're talking about ongoing delivery and sort of the controlled release. Well, actually, it seems to be the ratio of carbon to nitrogen, which is why I keep banging on about it, is the thing that's controlling the period of release of the nutrients. So basically, that carbon to nitrogen ratio, the higher it is, the longer the turnover of the microorganisms. And that is not just the carbon to nitrogen ratio of the material you're putting into the soil, it's of the fertilizer zone. Because, of course, the microbes in that zone, where the fertilizer is mixed in, it's actually the soil microbes that are working to doing most of the work breaking down the fertilizer and making the nitrogen available, or maybe turning more complex forms of nitrogen into those that can be taken up. We do know that organic forms of N can be taken up, but we know that a lot of ammonia and nitrogen gets taken up. So it's those processes. So carbon forms are the fuel for those sorts of processes, and you have a whole complex interaction of carbon use efficiency and respiration and those sorts of things that determine what availability of N there actually is to the plant in that whole turnover process. Now, what other elements were there? The nitrification inhibitor. When you looked at those graphs, the I in those graphs were all inhibitor nitrification inhibitors added in to those particular soils. So nitrification inhibitor had quite an impact, and particularly because the leaching challenge was applied to each of these soils. So so the way the growth accelerator trials will run was that you put the fertilizer into the soil, you allow, I think it was like 10 days of incubation. Then we leach the system with 1.5 pore volumes, and so vulnerable N tend to be lost. And then we grow out under, transplant seedlings into the pots, and then grow them for, I think it was like 40 or 50 days to the first harvest, and then a second harvest after 3 wetting and drying cycles. So yeah, I hope I answered some of that for you.
I think the next one's to Sasha. Were encapsulated liquid products tested? And what was the outcome?
Liquid products weren't tested. They were in another side project.
Yeah.
They're not part of this one.
Okay.
The encapsulating technology is not exactly encapsulating. We're combining the fats from the soldier fly with the frass to slow down the leaching potential of frass, but not all frasses, but specific ones, particularly ones that have come from poultry, were quite high in ammonia. So yeah, it wasn't what I call encapsulation technology. We weren't coating, we're just combining.
Yeah. Okay. What is the physical format of the BSF fertilizers tested?
Is that for both the amount of, sorry, what was the?
It just says, what is the physical format of the BSF fertilizer tested?
The physical, like, well, some of it was applied just as it was. Others were granulated. Others were pelletized. As I say, some were combined with other parts of the fatty acids to form a new product. And then obviously, Matt did a whole range of things that he's discussed with the larva.
Yeah, mine were not pelletized up. I'll say that straight up. It was sort of early enough stage research that the formulation in that form wasn't my target. It was how to get some of the other things right. But ultimately, you want a material that can pass nicely through an air seeder, I think, is a good target. And the pelletizing is a good process to achieve that.
Yeah. There's a question here saying, interested in the benefits of placing black soldier fly larvae in manure. Can this be done in a private facility? By that, I mean placing the larva in a manure of a holding yard, for instance. If so, would this result in a fly outbreak disrupting nearby residents?
Yeah, I can take that one, Janine, and I did answer in the chat there. But essentially, ideally, the larvae need to be kept in controlled environments, and that includes ensuring that the flies are enclosed and not free ranging.
Yeah. Okay. Yes, as in not out in the open. They need to be controlled. So,
Correct.
I think that's pretty much gone through quite a few of them at the moment, and we probably need to wrap it up because it is 1:05. And so yeah, and if anyone's got any questions, yeah, feel free to ring the researchers, taking into account that it's still being under review, and IP and a whole range of other things are still being reviewed at this present time. So I'd like to wrap it up now and thank everybody for their participation, and I hope you learnt some things about black soldier fly. Thank you very much.
Thanks a lot.
Thank you.